Hello. Okay. Um, Welcome from myself as well. My name is Nina Balke. I'm a faculty in the Material Science Department. And I have the great honor to introduce to you the speaker of this year's Davis Lecture, which is Professor Ramesh from Rice University. So if we consider this event and the caliber of speaker we are talking about, my first idea was to make a really proper introduction like you're used to when you have an important speaker. But then I paused and thought about Ramesh. I thought about his personality and what you might not know about him. He calls every student, postdoc, or colleague boss. He treats everyone working for him as a colleague and collaborator instead of an employee. And every free minute he has, he goes in the lab, asks for the newest data, and jumps around like a jumping bean if something exciting emerges. So clearly, a proper introduction like you're used to was not the way to go. And also, Ramesh asked me not to make a fuss when I introduce him. So I'm not going to tell you about all the great achievements he had in terms of scientific publications, awards, honors. They are countless to name in all the places he has worked for, which are very impressive. I'm not going to tell you about the impact his scholarly work has had and how often we expected that the next time they announce the Nobel Prize, it's going to be his name. So what I want to tell you about is that Ramesh affected many, many generations of scientists and touched their lives. This was very obvious when we planned this event, when many people in different stages of their careers came to us, said how excited they were for this visit, and told us how they met Ramesh in the past and how he has influenced their career and their life. Ramesh is one of the most passionate scientists I know, and I'm very happy for you to be able to see some of that today during the talk. So without further ado, I want to ask you to help me welcome Ramesh to the stage and hand it over to him.
Thank you. Thank you so much, Nina. Thank you. I think I have. Can you guys hear me in the back? Don't mess with the nuclear sub guy. That's all I can say. He's sitting in the back there. Thank you so much. First, thank you to Bob. Of course, for somebody like me, by the time I had gone into graduate school at Berkeley, Bob was already a legend. There were a whole bunch of people. Jay was in the same category, Subhash Mahajan. There's a whole bunch of people who were already in the Marvel Avengers category, And so Bob was already there. And so when Don called me about, 6 months ago, and he said, hey, I got an email, I think, from Don. My jaws literally, you guys have seen the Warner Brother cartoons. I'm a big Warner Brother fan anyway. My jaws literally dropped because, association with Bob Davis is something I cherish. So thank you very much, Bob, for this endowment. And hopefully you will hear something interesting, exciting, if not, no money back, okay? So I put together a new talk for this event. I also got a little bit bored, and I was giving my usual polar skirmions, which is a fun topic, which you won't hear about today. But I said, maybe you need to get a broader perspective, if you're not into CMOS, electronics, you should still take something away from this talk, okay? That's kind of the intent. I just moved to Rice University. Again, unlike many other people, I've had multiple midlife crises. And the first time I went and bought a Porsche, my wife was pissed with me. I said, dude, I got to drive one. But you go to the dealer, he said, no. Have you ever bought a Porsche? I said, no, I haven't. He said, I can't sell you a 911 because you don't know how to drive it. I said, I could sell you a Boxster. I said, okay. But then I had to go to Washington. I'm going to tell you a little bit about the Washington trip. And so I had to sell my Porsche, which I was crying, but I sold it. Anyway, my wife was very happy that I sold it. Then that happened. In between, I went to Oak Ridge for a year, which I thought was also part of this midlife crisis stuff. I got yelled at by people. I thought, okay, I'm done. I'm going to be a SUDI, go be a lab director, which is what they were preparing me for. When I went there, a bunch of people, and a couple of them are Nobel laureates, Professor Fiert, and you will hear a little bit about Professor Fiert. He's a 2007 Nobel Prize winner for the GMR concept. And he came to Oak Ridge to give one of the Wigner lectures. And he said, Ramesh, you look to be young. Why are you doing all this management stuff? Go back, do research. And a bunch of other people. Bob Dines, some of you guys know Bob Dines. He was the president of the UC system. Bob was a lot more open. He's a very close friend. He said, you've done a lot of stupid things. This was the most stupidest thing. Go back and do research. So I went back to Berkeley for about 8 years. And I figured, okay, now I'm past 60. I wanted to explore other things. That's kind of what we're doing. We're trying to set up a very exciting game plan, very focused on research. And Rice, for those of you who know, Rice is a very good undergraduate university. It is not too shabby on the research side. They won a Nobel Prize, for example. But we wanted to create a culture where you expect to win the Nobel Prize every year. You may not win it, but you expect to win it. And that's kind of the game plan we're pursuing. Okay. Acknowledgements of several people. Nina, where's Nina? Oh, that's right there. Nina, of course. What I've always tried to do, I come from a very poor background. We had to scrape and fight for everything. I tried to program some of that into the folks in my group. I never thought of them as my students or my postdocs, but mainly as my colleagues. I have a responsibility to make sure that they're successful. Nina has been incredibly successful at Oak Ridge, now as a faculty here. Lane Martin, Nina knows him very well. All of them, it's a whole bunch of people. For me, that's been the fun part. Not that I'm teaching them, but I'm actually learning from them. I will talk a little bit about this. I don't think you have seen this, so I'm going to talk a little bit about it. Our BML team, the Beyond Moore's Law team at LBL, the Dan Ralph group at Cornell has been very valuable. And of course, we're now beginning to work a lot with Professor Feert. If you ever have seen somebody do triple cross products, not a single cross product, but 3 cross products, Albert can do it, no problem. When he gave this Wigner lecture, he started doing this math. Half the people died, basically. Cross products are not that easy to keep track of. Dot products are maybe okay. So Albert is amazing. He has won the Nobel Prize. He's not satisfied. He says, I want to start a new area. The other person who I know is very much like Albert is Steve Chu. And Steve, again, won the Nobel Prize for quantum optics way back in the 1990s. And then he got into federal administration, and I had the opportunity to work with Steve. Acknowledge the support of DOE, the SRC JUMP program, ARO CHARM program. Where's John? Thank you very much, John. John was in the early stages of this. Okay, so this is a part which you might not have heard before. I had the opportunity of doing 2 stints. One in 2011-12, where I ran something called the Sunshot Initiative. I'm going to tell you a little bit about this. The second one was part of this president's transition team. Does anybody here know what a transition team does? Huh? Transitions, phase transitions is exactly right. That's right. Yeah. So every time there's a change in the party, Republican, Democrat, and vice versa, there's an early recon team that goes in, and typically they go into the agencies to find out what's going on, how do you transition? And the government is actually a very fantastic animal. You have a layer of federal employees without whom we'll be dead in the water, and so thanks to all of those Fed employees. And then there's the political component, which every party brings their own team. They come in, there's about 3,000 or so people who come in and overlay on that. So I was part of the energy transition team. Arun Majumdar from Stanford was the lead for that. It was mind-blowingly awesome experience. And we didn't sleep for like 3 months because it was so intense. But we had a lot of fun doing what we did. So if you look at the goals for this administration, 100% clean power by 2035. A lot of people think that's difficult. Not mission impossible. You don't need Tom Cruise for this, but it's not going to be easy. Just because of so much of embedded fossil fuel into our mix. Net zero economy by 2050. You need innovation and you need deployment at scale. It's not something that we as material scientists would always think about. Innovation, yes, but deployment is important. So the 4 big things that President Biden ran on was environmental justice, which meant that the stuff that you do as a federal government has to be just across the spectrum. And typically, if you're one of the poor people, you get impacted asymmetrically when there is a climatic event, a fire or a hurricane or something like that. Okay. That's the big part of this EJ. It was called EJ 40. 40% of the investment that you make has to impact 20% of the people at the bottom end of the socioeconomic spectrum. Manufacturing, supply chains, and jobs, you're already seeing some of those. It's called Build Back Better. That was the original name. Nobody liked that name. That's too dorky a name. Okay. Competitiveness. The United States absolutely needs to become more and more competitive. Our friends across the world are not waiting for us to do something. They're going to compete the heck out of us. So we need to start to compete with everybody outside. And of course, a big push was climate and foreign policy built into this. Okay, so with that, I'm going to take you back to what happened within the energy transition team. Okay. What we heard, and this was a big surprise to me, they said, you as the federal government actually did something useful for the nation once in a while. So why don't you guys do more Sunshot? And so I want to take you through what the Sunshot initiative was, what did it accomplish, what did it not do, and what were the lessons learned. It was in the original, the first Obama administration, Steve Chu was the Secretary of Energy. And for those of you who know Steve, Bell Labs, Nobel Prize from Berkeley at that time, he was very focused on climate change. He was the messiah for climate change. And so he was saying, let's go green on everything. In the second Obama administration, we changed the game plan. It became all of the above, rather than just go green, green, green. And so Steve kind of recruited me. I had no clue what these guys were doing, and he asked me to put the whole plan together. And it was an awesome experience, which is, if you dial back to 2010, solar electricity was 27 cents a kilowatt hour. For those of you who look at your electricity bills, which I don't, I have no clue what this is. But I was told it is very expensive. I could not afford to put solar on rooftops in 2009 because too expensive. And the challenge from Steve Chu was, the fundamental hypothesis was that when you bring the cost of electricity down to a parity number, the markets will take over. That was the simple, single hypothesis. In the case of electricity, in the wholesale market, if you go outside, it's about 3 cents a kilowatt hour. North Carolina, Duke Power probably sells a little bit lower. On an average, it's about 3 cents. We thought 3 cents was too crazy a number. Actually, Steve was getting a lot of heat from the solar people. People at National Academy, they were saying, you guys are smoking something in California. And we said, absolutely, yes, we are smoking stuff. But we said, there are no thermodynamic limits on what that cost could be. It was simply a factor of bringing the cost down by innovating on it. And so the challenge from Steve was that you had to bring the cost of solar electricity down from 27 cents a kilowatt hour. And we arbitrarily said 5 cents is a good number. Okay. And then what we did was to break it into all the components and went at it very hard. Okay. In doing so, we pushed a lot of innovation across the spectrum. A sense of urgency, for example. The parity was an important component. That number will show up again in the next slide as I talk about the Biden transition team. Competitiveness, global competitiveness is incredibly important, and we learned a lot of lessons. The one thing we learned was, by the time we started playing this game, manufacturing had already left the United States. Right now, 90% of solar panels are manufactured in China, although a lot of the innovation still happens in the United States. Our colleagues in Europe have the same problem. There's a lot of innovation, a lot of deployment of solar happening in Germany, but much of the manufacturing happens overseas. Okay. Now, very quickly, this is what I spoke about. This is coal, nuclear, and natural gas. By 2011, coal had already flipped. If you look at the marketplace now, it's all natural gas. Natural gas you can buy at 1.5 cents, maybe even lower per kilowatt hour in the wholesale market. Okay. Nuclear is a problem child. It's very difficult to bring the cost of nuclear down, although there's a lot of work going on in this area for one simple reason. Unlike other technologies where you have multiple pathways, you have a lot of time to go learn and learn and learn, the so-called learning curve. In nuclear, you only build 1 or 2, maybe 3 every year. And therefore, you don't have many opportunities to innovate and make it better. Okay? So the goal for I'll go to the old-fashioned way, was to bring this down by a factor of about 75%. But the challenge from Steve Chu was you cannot use policy as an instrument. And the reason was very simple. If you look at what the Germans did back in the 90s, early 2000s, they used policy, the so-called feed-in tariff. People who were raising pigs in middle Germany killed all the pigs and started putting solar farms. Why? Because the government was telling them, I will buy your electricity for 20 years at 54 cents, euro cents per kilowatt hour. And so the cost of electricity wasn't 54. It was only about 12 cents a kilowatt hour. So everybody killed everything else and put solar panels. But what happened was, in doing so, you had a whole bunch of people who had solar panels on the rooftops, and the grid was becoming unstable. So the Germans had to do a lot of gas turbines for so-called spinning reserve. These turbines are running around just on empty, but they're there to balance out the grid. Otherwise, it'll start to fluctuate. So in doing a lot of solar, in those days, 80% of solar was in Germany. But in doing so, their CO2 output actually went up. So one has to think through this really carefully. When you use policy as an instrument, you have to be really careful. So Steve was saying, we can't use policy. You can only use science and technology as a pathway. And it turns out that we actually met this target with about 2 years to spare, mainly because much of the manufacturing cost reduction happened in China. We did all of the other things within the United States. That fast forwards now to the main part of the movie. This is all the precursor to the movie. That fast forwards to 2020, the Biden transition team. A lot of people said, guys, you actually did something useful with Sunshot. People from Breakthrough Energy and so on. So they said, why don't you do a few more? And so we came up with this idea of Earth shots focused on the Earth. And I coordinated the writing of the Earthshot papers. Each one of them was like a prospectus. Okay. I'm going to take you through a few of them, and then we'll start to talk about this. We said, if you look at this energy climate change, if you believe climate change is indeed happening and man-made, there are a few things you could do. One is long-duration grid-scale storage. If you could get the cost of storage down to $30 a kilowatt hour, Tesla is building the plant for $120 to $150. So if you could bring it down by a factor of 3 to 5, then the world will look very different, because then wind and solar will absolutely take off. If you could capture directly from the air, this is a very tough problem because it involves overcoming entropy of mixing. Okay. If you can do direct air capture at less than $50 a ton of CO2, today it's about $500. Absolutely difficult problem. That's the carbon shot, and DOE is putting in significant amounts of funding. Billions of dollars of funding are coming out on this. Hydrogen shot is the parallel universe to carbon. If you could get hydrogen at 50 cents, I was pushing for 50 cents, Arun was pushing for like $1. Today it's about $5 a kilogram of hydrogen. There's a lot of metallurgists all the way from Jay who have done some fantastic work on embrittlement and stuff. Hydrogen is not an easy thing to do. But there are some nice new solutions coming out. Home shot was something I pushed for like crazy because it's a very difficult systems level problem. And the problem has to do with the fact that 38% of US energy goes into heating and cooling, and it's very difficult to reduce that energy consumption. So we were saying, how do you go from 6 kilowatt hour per square foot per year to 2 kilowatt? And I met somebody this morning or yesterday who was doing some awesome work. I'm forgetting his. This morning, that's right, on thermal energy. We don't pay much attention to thermal energy. Phonons are the bad cousins of electrons. But actually, you need to pay attention to a lot of heat transport. I think there's some lot of beautiful materials to be done. If you look at the four, each one of them has amazing amount of materials. So I would argue that the next 50 years is going to be incredibly important for materials innovation. And I hope to be alive for part of it, at least. The last one, which I absolutely had to fight with Arun, because Arun was saying, what are you talking about? It only takes about 5% of total energy. I said, no, it can go up to 30% of total energy. And we went back and forth. Our national security colleagues came in. They said, look, there is another angle to it, that if you don't have a good hold on next generation electronics, we could be importing components for the entire security apparatus from outside the country, which is a big problem. And that was this energy efficient computing. That's what we're going to focus on. Good, yeah. So that's where we begin our story. Why is this such a big problem? The chart that you see here was a calculation we did back in 2014-15 timeframe. What it shows is primary energy fraction as a function of time, and you can see the red arrow taken off essentially exponentially. That's because of the deployment of electronic components in AI, machine learning, IoT. And those things are going up exponentially. So if you do nothing to today's electronics, approximately 20 to 50 picojoules, maybe 100 picojoules per logic operation, because of this exponential deployment, by 2030, 25% of primary energy coming from burning coal, for example, at a nuclear plant, can go into computing. And we said, hey, we need to reduce that from picojoules to attojoules. How does one go about doing it? Keep in mind, this is still not thermodynamic limit. The so-called Landauer limit is kT log 2. Okay. And the Semiconductor Research Corporation came out with their own study, and it basically says the same thing in a different way. It plots the compute energy, which is electrical energy, as a function of deployment. By 2030, they were saying about 10% of compute energy is going to be spent in all of computing. That's 10% of electrical energy, and there's a 40% conversion factor from primary to electrical, so that's approximately 25% of primary energy. And therefore, there is a complete need for a new way to do computing, a very highly energy efficient computing. Hello? Oh, there you go. Okay, so with that, we're going to go deeper and deeper and deeper into this question, hopefully end up with spin-orbit coupling. Okay. So if you look at, again, data from Intel, if you look at this chart, it shows heat output in watts per square centimeter as a function of years. This is the original bipolar. CMOS is here. You could see they all have the same trajectory. And so there's a recognition that you need to go to a new approach for computing. The question is what? This came from these two fine gentlemen, both Nobel laureates. These guys did not win the Nobel laureate, but they should have won the Nobel Prize for what they did. Intel, Fairchild, all of them came from Gordon Moore and Bob Noyce. The question is, what is going to happen there? And our hypothesis is that you can go do it at the circuit level, architecture level, but being materials physicists, we're saying, we need to go to physics and see if that works. Quantum materials are going to be a possible pathway to solve this problem. Let's use this. So let's begin with a little bit of thermodynamics. We think that you can go from kT log 2, which is basically what happens, or nkt log 2 for electrons, uncorrelated systems, to kT log 2. How does one do that? If you write down the very simple thermodynamic equation, you could see that the energy is just F plus Ts, and the entropy term is K Boltzmann constant, log of W, where W is the degree of freedom. For an uncorrelated particle like an electron, that's basically, 2 power n. And so you can go in and calculate the T delta S, and so you get nkt log 2. And this is just from textbooks, nothing dramatic. On the other hand, if I use something like a ferromagnet or a ferroelectric, where there's internal order in the system, we could have a correlated electron system as well, where there are internal degrees of freedom that basically align all the spins, or the dipoles for that matter. Then you can start to have a scenario where the total energy dissipation can be just kT log 2. And that's the fundamental physical hypothesis. One can then capture it in the device form. That's a schematic of a standard CMOS device. And this kT log 10 divided by the charge is 60 millivolts. That's called the Boltzmann tyranny because that comes from the Boltzmann distribution function. For an ideal CMOS device, that slope of this curve is always going to be 60 millivolts per decade. In reality, it's actually larger, typically about 80 or 90 millivolts. Now, a few years ago, about 10, 12 years ago, a colleague of mine, Saif Salahuddin, and I, actually, he was the one who was driving the physics. I grew the materials. We said replacing the gate of this CMOS channel with a ferroelectric can invoke something called negative capacitance. I will not be talking much about negative permittivity or negative capacitance. It's a very interesting and controversial topic in condensed matter physics. But we showed that indeed you could do that and reduce that slope to something less than 60 millivolts per decade. And so this is a big challenge right now. The other way to solve the problem is to say I go to a ferromagnet where I have my spins aligned completely, or a ferroelectric where I have the dipoles, spontaneous dipoles aligned completely, or even more interesting, I could have a multiferroic material which has a spin and a charge degree of freedom. They're both coupled to each other. For the next 20 minutes or so, we're going to be talking about multiferroic materials. So about, again, 8 years ago, as I was just coming back from Oak Ridge, literally a month after I came back to Berkeley, there's a fellow who now co-founded a company with me called Kepler Computing. He said, hey, we saw this paper that you guys wrote. We think it's very interesting. We want to give you money. This is like seeing God, okay? You've never heard somebody, I mean, some of you guys maybe, Shrikant maybe has people giving money. Industry guys coming and telling you, we want to fund you. We said, yeah, okay, that's great. And so what they wanted us to do was to take them through how this material would work. Nina worked on it for her 2 years of her fellowship. So this material is bismuth iron oxide, which is a very fascinating material. So in terms of how this would work, you have a voltage input with a metal wire, for example, that would manipulate the magnetoelectric multiferroic material. You would switch the polarization. The coupling between the magnetism and the polarization, the spin and the charge degrees of freedom, then changes the magnetic state. Okay. Then you do all of your logic operations in spin space. You can do spin-based logic. Then you read it out with something called the inverse spin Hall effect. All of this is fine. Physics-wise, there's nothing crazy here. The only problem was if you wanted to get to our magic number of an attojoule, that voltage had to come down to 100 millivolts. For those of you who are EE people, you have done your own EE classes or condensed matter physics classes. Basically, it's 1/2 CV squared. That's the energy in a capacitive element. So if the capacitance, which is basically function of the material properties, the only other knob that you have is voltage. So the entire premise for this kind of work is to reduce the voltage. Today, CMOS works at about 1 volt. Our goal was to initially get to 100 millivolts and then get to 10 millivolts. How does one design materials? For this is the question. Okay. So the challenges for materials physics was converting from charge to spin, which happens here at 100 millivolts. And we're not very far off. I'll show you some data on that. Converting from spin to charge is a nasty problem. And I'll show you some data on that as well, as to where we are. We're not there by any stretch. Where's Rejwan? I can't see Rejwan. Yeah, there she is. She hopefully will be working here on that. All right, so energy scales. Now, one of the questions to ask is, okay, what's the deal with this energy scale? This is a simple slide, but it actually is kind of illuminating. This is data from way in the past. This is the so-called colossal magnetoresistance effect, which is something that we discovered back in 1990s. You have a material which has a resistive transition like this, apply a magnetic field of 6 Tesla, you go from the red to the green. You apply an electric field of 400 kilovolts per centimeter, you go from the red to the blue. Okay. And this material is a very fascinating material by itself. It has regions of ferromagnetism mixed in with regions of antiferromagnetism. Now, if you look at this, you can calculate the magnetoresistance and the so-called electroresistance. But here's the most interesting thing in this whole picture, is that there is some, if I look at the physics of the magnetic field, and this is just from a textbook, right? This is just Ampere's law. If I have a wire like this, I have a magnetic field given by the right-hand rule. To get a field of 6 Tesla at a distance of a micron, I need to run something like 30 amps. And first, blow up the wire. Second, blow up your bank because you need a big battery. The electric field, on the other hand, scales with the dimension. So the electric potential scales with the dimensions. The field is fixed at 400 kilovolts per centimeter. And so if I have a 100 nanometer thick film, it's only 4 volts. If I have a 10 nanometer thick film, it's only 400 millivolts. But if I go to a millimeter substrate, of course, it's 40,000 volts. So the key message was, if I have capacitive devices where electric fields can be very useful, I can reduce the voltage. But if you're an electrical engineer, you say 1/2 CV squared is very important, so I can reduce my energy this way. And this is the primary reason to say, how do I manipulate a magnet with an electric field? That's not the conjugate variable. The magnet would be a magnetic field. So that brings us to materials. Okay? Now, we are oxide people. There's a lot of oxide people here in the audience, so I won't spend too much time. These are the materials that we play with. These are perovskites. You have the oxygen coordination, you have the B site, and the big atom is the A site. The oxygen are the red atoms. The fun part with these materials is you can basically swap out the various cations. You can tune the electronic structure. These are the 3D electrons in this ion, and you can make them do many things. So you can really play a lot of games with the structural distortions. Epitaxy is a big attribute of this. So you can tune many parameters. Okay. The next part of it is, of course, our model system. Bismuth ferrite is a very, very heavily studied system. And, come on. When you apply an electric field, the polarization, which is this green vector, switches by 180. For about 10 years, there was a lot of discussion in the field. What happens to the magnetism? That magnetism is MC. I will not go into the details of this MC, but it is a small canted moment that happens because of another quantum mechanical effect called the Dzyaloshinski-Moriya effect, which is related to spin-orbit coupling in the transition metal ion. Okay. So the big question was, is this changing? We now know that it does indeed change. It switches by 180 degrees. And I'll show you some beautiful data in just a second on imaging this. We have to be also cognizant of material synthesis. For poor people like myself, we use something called laser MBE, which is pulse laser deposition in an ultra-high vacuum environment. Ridgewan will have something like this in her lab very soon, but you can start to do in situ diagnostics. You know, between Lane and myself, a whole bunch of people, we do quite a bit of pulse laser deposition. And in doing so, you can start to build these artificial heterostructures, very similar to what our semiconductor colleagues would do with gallium arsenide. I mean, they've just done some fantastic stuff. At least 2 Nobel Prizes have come out because of that. In the gallium arsenide semiconductor area. And so we can now start to make these with atomic scale precision. We can manipulate terminations by inserting not just 1 unit cell, but half a unit cell of materials. For example, we can put 1.5 unit cells of strontium ruthenate, convert the termination of these layers from A site to B side. We can play a lot of surface chemistry games with these materials. That's been a big development in the last 10 years, and you all have some fantastic people here doing such work already. Okay, that brings us to a key piece of data, which took us a while to get to because we wanted to make sure that we actually got this right. So if you take this bismuth ferrite layer, which is here, if you put a spin valve, which is a ferromagnet, metal ferromagnet, on top of it, the ferromagnet at the bottom will couple magnetically to the multiferroic. And in doing so, you will create something called a GMR, a giant magnetoresistance spin valve. This is what Albert got his Nobel Prize for. And you can see that the resistance can be modulated by a magnetic field. Not a big deal. This is not the big discovery. But what is interesting is that the bottom layer, which is this ferromagnet, is coupling differently than the top layer. So you get something that looks like a split hysteresis loop, and more, we can manipulate it with an electric field. You can see the green and the red are different by applying different polarities of electric field. So in principle, what you're doing is manipulating the magnetic state of this layer, magnetized this way versus this way, by applying an electric field. Okay, with that, you could say, what else can we learn about this? The first question was, how does one go from 2.5 volts down to 100 millivolts? And we still don't know completely how to go to 100 millivolts. But we know that one can tune Landau potential by chemical substitution. So you can use crystal chemistry, very classical approaches. Take bismuth out and put lanthanum into the structure. And you can tune the double well. And that indeed impacts the hysteresis. This is a 10 nanometer of lanthanum substituted bismuth ferrite, where the corrosive voltage is 200 millivolts. We now know that there are other materials like PZT where you can get very close to the 100 millivolt number. We also know that lattice dynamics plays a big role in the switching properties. And unlike in a ferromagnet, where you don't have to worry about all of this stuff, in a ferroelectric, mechanics plays a big role. Which means if I have a film that's stuck to a substrate, that film will switch differently than when it's released from the substrate. That's what this data is showing. The release sample is switching a lot more easily because the lattice plays a big role. Interfaces play a big role. That's what this is saying. I can tune my interface electronic structure by putting in additional layers. Just a couple of unit cells of different materials can tune all of this. Okay. Let me skip through some of these because I think there's too much detail. What we did was then to build the full device that Intel wanted us to build. And this took us, again, a few years. Our friends in Spain actually built this structure. So we could switch the BFO back and forth with an electric field. We could read that out with the inverse spin Hall resistance, or the current that comes out of it. That resistance changes itty-bitty, but it's measurable. With the lock-in, it's not a problem. And you can see that it switches at about 500 millivolts for about a 20 nanometer thick sample. And you can keep doing it back and forth with this process. Lots of issues with this. First, this interface between cobalt iron, which is the ferromagnet, and the multiferroic is a very bad interface. It corrodes very easily. So we were asking questions. How do I enhance the spin-to-charge conversion? Can we even do without the ferromagnet? So in the last 10 minutes, I will tell you a little bit about what we have done on this. Actually, this is perhaps very exciting to me. Let me just summarize. This is where we are. We know that we can go to about 10 to 20 nanometers. We still don't know how to do careful measurements at a few nanometers. Electrical measurements is not that trivial. That's a big challenge for us, especially in real devices. But we know that the ferromagnet will switch back and forth. This is measured using photoemission microscopy at about 500 millivolts, maybe 200 millivolts. 100 millivolts is still a challenge. Okay. All right. So with that, I'm going to show you the last part of my talk, which is the spin-to-charge conversion. So if you remember, I showed you one picture which said I go from charge to spin using a magnetoelectric. Now I have to go back and read the spin out as a charge. Why? Because reading a spin is not that easy. You have to use optics, and it doesn't scale very well. It's much easier to read out a charge signal or a voltage signal. So the conversion of spin to charge at 100 millivolts requires immense amount of innovation. It's not trivial. And so the question is, what can we do about it? I'm going to take you through a very quick summary of this, and then we'll finish up. Sorry about some of this stuff, but it's just the pedagogy behind the spin-to-charge conversion. If you have a ferromagnet which is connected to a material, it turns out that the efficiency is of this conversion between a spin to a charge is measured by something called the spin Hall angle, which is given the notation theta. It is the ratio of the spin current to the charge current. Okay? And the spin orbit torque efficiency, psi, is just the interface transparency, which is typically around 1 times this theta value. So if you look at materials, people typically have used materials which have large spin-orbit coupling. And so if you look at this chart, it looks very complicated. It is very complicated. But you look at the spin-orbit torque efficiency, there's very few materials which have above 1. Platinum, for example, is 0.1. Okay? And if you look at the physics behind this, the spin conductivity, sigma, has got a lot of different terms, but one of them is this omega, which is a spin-Berry curvature. Okay? That's given by 2 terms. One is the degeneracy of the electronic band structure, and that's the difference in these 2 energy scales. You don't want to be very different, okay, because that goes into the denominator. The numerator is basically the matrix elements for spin-orbit coupling. So if you have materials which have heavy elements, platinum, tungsten, tantalum, all of them have large matrix elements for the spin-orbit coupling. That's what people have used out here. And we were saying, guys, it would be much better if you used oxides. Of course, there are some materials like bismuth selenide which also work very well. Okay, so we went back to our standard game plan, which uses epitaxial interfaces where I can manipulate not only the electronic structure, but the spin structure and the lattice at the same time. And so we grew one set of materials, in this case, lanthanum strontium manganite is a ferromagnet, and strontium iridium oxide, which is very, very interesting topological insulator, which has some very interesting electronic structure effects. And you can see that this efficiency is changing significantly as I reduce the thickness. It is actually going up as I reduce the thickness below 10 unit cells. If I make it polycrystalline or with a normal ferromagnet, that efficiency actually is lower. So this epitaxial structure has given us a pathway to look at something very different. And so we said, okay, if that's the case, can we now go from this structure, which I showed you 10 minutes ago, where I have the full stack, the red layer is my ferromagnet, and I look at the ferromagnet magnetized this way versus this way, and read it out as a spin Hall current, going this way or this way. We said, what happens if I completely ditch the ferromagnet, and I put my spin orbit coupled material directly on the multiferroic? So instead of using a ferromagnet, it's like you sending money, let's say, as folks in India or any other part. If you want to send money to India, you might as well send directly from dollars to rupees. But you could send it to Japan, send it as yen, but everybody will take some tax out of it. So instead of going from the multiferroic to the ferromagnet and then read it out, we're saying, maybe I can read it out directly. And indeed, it works very well. So the experiments, this is still unpublished because we're haggling with a bunch of referees. And you have the ferroelectric multiferroic material. It has the polarization, which is shown by the red arrow. You switch it, it goes that way. Our hypothesis was that the magnetism, the antiferromagnetism, also changes, and it does. And therefore, the spin current, total spin current, also changes from positive to negative as I switch my polarization state. All right, so, good. So I had a fantastic physics student. He's unfortunately not a professor. He's absolutely professor material, but he's now making $250,000 salary at McKinsey. But Eric did a beautiful set of experiments with another postdoc, Lucas Correda, who's drowned now. The experiment was to put this bismuth ferrite, put platinum as electrodes. Then we said, let us simply heat the platinum. And when you heat it, basically it starts to put out something called a magnon. These are just spin waves, okay? And you can then pick up that magnon as the inverse spin Hall effect using the other platinum. This whole effect is called the spin-Seebeck effect. If you're into spintronics, the spin-Seebeck and the spin Hall effects are very heavily studied right now. What Eric found and Lucas found was that they could indeed get an output voltage of about 50 nanovolts. Not a huge value, but they could measure it. But interesting was that the polarity of that voltage or the current was changing as I switched my ferroelectric, which is white here and it's black here. You could see it goes from the red to the blue. They also showed that it is not coming from the ferroelectricity. What they showed was that this hysteresis in the non-local spin Hall voltage came from the magnetic part of it by comparing the bismuth ferrite here to lead titanate, which is a classical ferroelectric, and lead titanate has no non-local effects. That non-local voltage comes only from the spin component of the material, and only bismuth ferrite has those. Okay, maybe I should skip these last few slides, get to my conclusions. What we then showed was, if I replace platinum with our oxide material, this is strontium iridium oxide, it's a topological insulator material, our output voltage goes up by about 20 times. We go from 50 to 100 nanovolts to now microvolts. Okay? And these are two different measurements for this. And it's qualitatively consistent in multiple measurements. What we then showed was, by going from 1 micron spacing, if I simply change the spacing from 1 micron down to about 10 nanometers, indeed, the output voltage goes up from nanovolts to about 10 millivolts. And if you remember, we started by talking about 100 millivolt as a required output voltage to start to think about real devices, and we're not too far off. We think there's a whole bunch of these kinds of materials. Materials like bismuth selenide, strontium iridate, other oxide materials which have very large spin-to-charge conversion efficiencies. So we are up to our eyeballs into looking at these kinds of materials. With that, I'm going to slowly finish up. I don't know if there are physicists in this audience, but this is a physics outcome that is very exciting to me, which is, if you look at these kinds of epitaxial materials, typically these magnons are diffusively transporting, meaning they are like meandering all over. There's no coherency to their motion. But our hypothesis was that if you go to low temperatures, take away phonons from the material, and go to these perfect interfaces, maybe we can have coherent magnon transport. And if that can happen, a lot of things like spin superfluidity, which has been debated in the physics community, but nobody has seen it yet, can be possible. So we are very excited by these epitaxial heterostructures being a pathway to do something dramatically different than today. So what are we trying to solve? With the last two slides, what are we trying to solve? This is the engineering version. This plot is from Intel. On the energy scale, we want to be somewhere here. Attojoule is somewhere here. On the latency, we want to be around 100 picosecond. Your static RAMs in your memory device are all working at about 100 picoseconds. Okay? With multiferroics, we think we can get to 100 millivolts. That's where we would get to 1 attojoule. Materials with very large spin orbit torque. If you remember, way at the beginning, I talked about spin orbit coupling being an important parameter. That plays in both the multiferroic work as well as in the spin orbit torque materials. We are now beginning to think, oh, it may be possible to get to these very large effects. Okay. All right, so with that, I will put up a slide, which is something that our LBL team is working on. We have now gone into a mode where we don't do the physics or the materials separately. We do all of them together. And we call that CMOS plus X co-design, meaning you're working with our circuit people, architecture people, everything together. And so you can see the infinite loop there. We keep going back and forth. Our underpinning, of course, is the double well structure. We can use these to create logic and memory, which is a very important pathway to get to low energy compute, or negative capacitance FETs. I will finish up by showing you a short movie that one of my twins, he's a design person, and hopefully this captures it. The idea is you can take a problem at the global scale, looking at economics at the very large scale, $2 trillion market, go into AI and machine learning as the fundamental big technology driver, go to energy efficient computing, but you don't have to stop there. You can go all the way down to new materials. You don't have to stop there either. You can go to new physical phenomena, ending up, of course, this is the hydrogen atom, which is kind of the simplest prototype, where you can actually start to use the principles of condensed matter physics, advanced material synthesis, to solve a problem at the global techno-economic scale. And with that, oh no. Yeah. Thank you very much once again for the opportunity to chat about this. Happy to take questions from you guys.
Do we have any questions?
always a student.
Yes.
He just happens to be a professor who is a student. Yes, Jay.
What an exciting time.
Thank you. Yeah.
What's the role of surface interface with steps?
Yeah, I mean, this is a great question. I think I went over it probably a little bit quickly. If you're only looking at 5 nanometers in oxides, 5 nanometers is 10 to 12 unit cells. And therefore, every unit cell matters. So if you have one missing atom, you've lost something. And therefore, you have interface traps, for example. Everything that our semiconductor friends do so very well. CMOS lives and dies with all of these things. That will all become important. So Schottky barriers become important. If you have steps at the interface, that's what I think Jay is talking about. If you have steps, in the case of these oxides, you can invert the surface. You can go from the A site to a B site. And so you can change the properties. You can create antiphase boundaries in your material, which could all become bad for the switching behavior. You can have structural distortions, octahedral tilts, for example. All of them will start to play a role. So we are telling ourselves that the era of just growing a 100 nanometer thick sample and measuring some loop and publishing a paper is over. I think we really need to start to treat these materials like our semiconductor colleagues would do. Very, very sophisticated electronic materials. Does that make sense? Yeah. You guys have a lot of oxide people here. There are 3 people there in the back who do MBE. So for the students, you can go crazy. Yes? Yeah? Yeah?
For your measurement at room temperature,
Mhm.
room temperature non-local. Well, so for spin feedback in the phonon driver magnums,
Mhm.
right? So the magnums propagated without phonon.
Yeah.
So one of the slides is showing that at low temperature,
All of the data you saw is room temperature.
room temperature.
Yeah,
So,
yeah.
So do you consider that longitudinal spin feedback give you a non-local signal or just a transverse spin feedback?
By the way, this is a great question. The honest answer is we're not sure yet. When we go to these low temperature measurements, mainly because our structure has the source and the detector this way, and this is primarily measuring the transfers. But we actually have no clue what the magnons are doing. So one of the things that Albert has been pushing us is say, visualize the magnons. How do you visualize? It's not that easy to visualize that. So there's some work to be done there. So if you build a vertical structure, there's an advantage. They can only go this way, right? And there it's no more, it's only longitudinal, not transverse.
If you apply temperature gradient like horizontal, you may have still have some unintentionally vertical temperature gradient again, you longitudinal species.
That's right, exactly. We're getting some. I think we're getting some average value of the longitudinal and the transverse effects. Yeah, we don't have that. But these are literally the first measurements of these materials. Other people have done, iron oxide and garnets and stuff. So. Dude, louder. Old people in the audience. Yeah. That's a great question. Let me repeat the question. Why do you think that the interface is transparent to the magnons? So the way we think about this is that you heat up the material, and like he was talking about, you create these magnons driven by the phonons. Okay. And then those magnons propagate from the hot side to the cold side, and you pick up some of them, right? And so the magnons are basically a spin wave. So you have an accumulation of spins in some sense at that interface. That gets converted by the spin orbit material, platinum or strontium iridate, and you read out a voltage signal that's corresponding to the spin to charge conversion. Does that make sense? Good question. The answer I gave you is a vanilla version. This is going to be a lot more nuances to it. Yes?
Thermal implication, when I work with regular Intel or something, somebody that I work with thermal cooling of electronic, we always worry about the thermal implication.
Yeah, by the way, thermal all comes from I squared R, right? But if you go to voltage-driven devices, you still have, because you're still getting out some current flowing back and forth. But the hypothesis is that if you go to lower voltages, everything will come down, And so you are going to go to lower current based devices. I squared R will be progressively smaller. Yeah, but thermal issues are the unsung issues with this stuff. Yes, sir.
Great talk. I have a question. So, things that we covered so far with our electronics systems, right? So, talking about gigahertz, terahertz, kind of thing. What happens if we scale that maybe in the optical regime, so in the 10 raised to 15? Is there an implication for that?
Yeah, we have this whole business is kind of pegging to conventional electrical-based electronics. Yes, there's a whole bunch of people. There's a lot of people here who have done some fantastic work on photonics. Right? In principle, you could do photonic computing. There's a lot of work going on. The question is the energy consumption there significantly lower compared to these kinds of approaches? That is out for question. There are bigger experts in photonics here than myself. And so my impression is that it is not going to be as energy efficient as, but the ease part of it is you don't do much of I squared R, there's just optical connections. But I think the energy consumption is still higher for those kinds of devices, approaches.
I don't see any more hands. Ramesh, it was a blast.
Thank you.
For taking 2 days.
Absolutely. Most welcome. Yeah, it's been most fun, educational.
I
Yeah.
want to give you this little token to remember the trip by.
Thank you.
And thank you again for a fantastic talk.
Thanks. Yeah. Sunshine.